Hi, I'm Maria Elias. I'm a quantum physicist, and today I'm visiting Harvard University. I'm going around some of the quantum labs here, and I want to show you around one of the neutral atom quantum labs where some really exciting experiments have been happening recently. So come join me. This is the Jefferson Physical Laboratories, where the lab that we're going to look around is. And here at Harvard, there is a big effort to do experiments with neutral atoms in a research group run by Mikhail Lukin. And the group works on various aspects of neutral atom quantum technologies, including an effort towards building quantum computers. And one of the biggest problems with building a neutral atom quantum computer has just been solved by one of the groups in this lab. So let's go take a look at what they've done. I'm here with Tim Guo, who works in the neutral atom quantum labs and is going to tell us a bit about the experiments before showing us around the lab. So hi Tim, thanks for showing us around today.
Hi Maria, nice to see you again.
Yeah, good to see you again. So I actually know Tim from many years ago when he came to visit Magdalen College, where I did my undergrad in Oxford, and Tim was visiting from Berkeley. Can you just tell us a bit about yourself?
I am a PhD student at the physics department at Harvard. I work under Professor Mikhail Lukin, and we're building a second-generation neutral atom array quantum computing system.
What is a neutral atom quantum computer?
For quantum computers, there are different technical routes to achieve that. They're like this trapped ion people. This actually first started in the 1990s, and the first demonstration of 2-qubit gate was a trapped ion. And you guys at Oxford, you have David Lucas there, amazing work. And then there's also superconducting qubits, which really got very popular in the 2000s, and Google and IBM are using those. We are using a different route, which is a sort of a new candidate for qubits, which is neutral atoms. So unlike ions, atoms doesn't get net electric charge, and we trap them using tiny focused laser beams, what we call optical tweezers. So each optical tweezer is like a tightly focused laser beam, and each tweezer we trap one atom, and then we form an array, and this array of atoms is our qubit array.
You mentioned that you've been working on this second generation array of these neutral atoms. Can you tell us a bit about what the first generation was and what's been happening in the research group here to do with neutral atom quantum computing?
Yeah, so basically the first generation atom array experiment under Professor Mikhail Lukin's group started around 2016 and 2017. And that was actually the sort of a first experimental efforts in neutral atom quantum computing that started this trend of recent years of neutral atom quantum computing effort. They were basically doing multiple experiments, like how to assemble a defect-free atom array using optical tweezers and then the electrical controls. They also demonstrate using atom arrays to do analog quantum simulations. So not gate-based digital quantum computing, but using the interactions between atoms natively to do some simulations of some many-body physics. And then recently, in the past 5 years or so, we see huge progress from their lab in digital quantum computing. They demonstrate very high fidelity to 2-qubit gate, which is 99.5% fidelity or higher, which passes the surface code threshold, and is really pushing the neutral atom array to the frontier of the quantum computing race, so-called. So now our 2-qubit gate fidelity is not much worse than trapped ions or superconducting qubits. And we also have a very scalable system. They demonstrate hundreds of atoms being controlled and staying coherent. And they also show that you can move atoms using the optical tweezers to drag atoms around. That's actually key, because in that case, and you say you have an array and you want to entangle the atoms on the two sides, you can just move them around, entangle them, and then move them apart. So that's a really enabling very advanced connectivity here. And they recently also demonstrate some error correction results, encoding surface code logical qubits or something like that, and demonstrating pass threshold experiment. So yeah, they are really huge progress and really pushing the frontier of atom array system.
Yeah, so to summarize a bit, the first atom array experiment demonstrated some of the key ingredients to build quantum computers. Partly it's this accuracy of the gate operations, which was this 2-qubit gate fidelity, showing that they can get high enough accuracies to do the error correction process that we know will be essential to reduce noise, reduce errors in quantum computers to get them to be useful. And another limitation is the scale, and they showed kind of implementing this on a large scale, an array of many of the qubits. And the other limitation is connectivity, and they showed this moving of the atoms to achieve the connectivity. So what are some of the bottlenecks or limitations of a neutral atom called computer after building those components that were demonstrated in that first array?
Yeah. So I would say this scale and this 2-qubit gate fidelity is still limiting us. So if we can push them higher, of course, it will be much better, right? But now, because of those are already getting quite good, we're now seeing a new bottleneck, which used to not be a bottleneck because our size is not large. This bottleneck is starting to be more dominating, and this bottleneck is really qubit loss. So this is kind of unique to the neutral atom platform, because in trapped ion system, ions can stay in the trap for like long time, like hours or even like days, like indefinitely lifetime. And superconducting qubits, like those chips, they just like are there. You don't lose them. Of course, your qubit can get out of your qubit subspace, but you don't lose them. Whereas in the neutral atom platform, because the atoms are neutral charge particles and we use a laser beam to trap them, the trap is actually quite shallow. So any sort of disturbance, like for example, a background gas particle collide with it, it will kick the atom out, so we lose the atom. And if we do entangling gates, there's also a finite probability of the atoms getting lost. If you image the atom, there's also some finite probability of losing the atoms. So all of these can contribute to atom loss. And if your atoms are lost, your computations basically just end, right? Because if your qubits are mostly gone, then there's no way to carry the computation. And so far, the way to reload the atoms, like to load atoms back to the tweezers again, are very destructive. So say you have some quantum information still being there, like some atoms are still staying there and they carry some precious quantum information. Now you want to reload the empty tweezers with new atoms. For the existing architecture, if you do that, the remaining qubits quantum information will get destroyed completely.
Right, so if you try and solve the problem of the atom loss by reloading some of the qubits, you will accidentally destroy the coherence in the rest of the qubits, and so it doesn't solve your problem because you can't then continue your computation.
Exactly.
So what have you been doing with the atom array 2 that I believe has gone some way towards solving this problem?
Yes, thanks for setting up the question for me to answer this. So for atom array 2, we're precisely trying to address this issue. We try to develop a way to reload the atoms without decohering the existing atoms. So in a sense, we can do this continuous operation, which means that like if you think about the traditional way, they basically run some experiments for like say 300 milliseconds or so, right? And then your atoms get lost and then you cannot carry on the computation. So basically it's like a computer that runs for 300 milliseconds and then you need to restart and then run it again and then restart, run it again. So here we have a continuous operation mode where we get some atom loss, but we can replenish them without decohering the other quantum information. So we can really like keep this computer on for a long time, like even to the hours time scale, and then keep operating this machine for a long time without needing to wipe out all the information ever.
You've managed to create a method that lets you keep reloading these atoms to deal with the problem of the atom loss, whilst also not destroying the rest of the information. And that means that you can operate in this continuous way, in the sense of being able to keep that information, in principle, staying robust, even as you deal with this problem of the loss.
So we like to think about the scalability in two axes. One is the temporal axis, one is the spatial axis. Spatial axis just means we have more qubits, so we have like 3,000 qubits, and temporal axis is this continuous operation, which enables us to run deep circuits in quantum computing. So we demonstrate this new platform with these two scalability axes already pushed forward, right? Like pushed to the frontier. It would be nice to show with a continuous operation some like deep error correcting circuits that we can run. Like for example, we can think about like fault tolerant algorithm.
And you've just had your paper published in Nature, right?
Oh.
So congrats.
Thanks,
on that.
I'm very happy.
Yeah. So maybe now we can go have a look around the lab and see this experiment.
Cool.
Let's go. Now we're here in the lab. So Tim, can you please show us around and tell us what's happening?
Cool, yeah, this is our lab. And everything happens on this optical table mostly. And I'll show you the vacuum chamber here. We have a lot of laser system, and our lab is really using lasers to shoot at atoms. So we have a lot of laser systems here. So here, this is our vacuum chamber where all the science happens. So we have two chambers. One is here and one is there. The atom will come from here. They will be heat up, and then they will have a lot of active vapor. And then we use lasers to pull the atoms down and trap them. And they will be formed here, a cloud of cold atoms. And then we use something called an optical conveyor belt to transport the atom from here to there. And this is actually the key to our continuous operation, so that the atom cloud is far away so that it doesn't destroy our quantum information. But basically, our optical conveyor belt is like two laser beams that are counter-propagating, and they can move the atom from one place to another place. And we actually have two of those optical conveyor belts, but that's a technicality. And then most of our science is done in this chamber. This is a glass cell. I don't know whether you can see it, but it's inside this black structure. And then here we have a microscope objective, which is a custom-made objective that we ordered from an optics company. And then that is used to image small things. So in our case, we're imaging atoms, individual atoms. So we have an array of atoms, and this guy enables us to see each individual atoms clearly. And then the light emitted by the atoms will be going through this optical beam path, and it will end up in this camera, where it's a really sensitive camera to collect the photons of the atoms. Yeah, so this is this side. We can go to the other side. And here our lab mates actively working. It's our nice movie that we have. And then here, this is the other side of the table. Here we have the tweezer beam path. Each atom is trapped by an optical tweezer, which is a tightly focused laser beam. And this is our beam path to focus the laser down using this microscope objective into this vacuum chamber to trap atoms. So these two magical devices can generate like thousands of optical tweezers, and then we can trap each atom into a tweezer. And then this is a beam path for the optical conveyor belt going into the chamber like this, and then there are two beam paths like this to transport the atom from there to here. And then again, this is our vacuum chamber, which is held at very low pressure. It's about 10 to the minus 14 of atmospheric pressure. So it's quite nice. Yeah, that's it.
Do you want to do a wave? So thanks for joining on the tour of the Harvard labs. Hope you enjoyed. If you want to see more quantum science and tech content, then subscribe to my YouTube channel. And until next time, Harvard.
Here we are at Physical Laboratory. Hi.
Hey. Hi, I'm Maria Violaris. I'm a quantum physicist, and today I'm visiting. Hope everyone enjoyed learning about your experiments.
Thank you.